Today we will talk about joint variables. This is part 3 of a series of videos on joint random variables. The goal here is to explore properties of conditional distributions. So let's set up. Let x and y be two random variables, and we will assume, for simplicity, that both x and y are discrete or they are both continuous. In the setting, let script x be the set of values of the random variable x and script y be the set of values for the random variable y. Then px comma y will be the joint PMF of x comma y if x and y are discrete, and fx comma y is going to be the joint PDF of x comma y if x and y are continuous. Then we can define the marginals, for example, p sub x, which is going to be the sum over all y's inside script y of px comma y. Similarly, the marginal with respect to x in the setting of the continuous random variable is going to be an infinite integral. We can similarly define the marginals p sub y and f sub y. The conditional distributions are defined as follows, where the conditional x given y is the probability of x and y divided by the marginal of y at y. The conditional of y given x is defined similarly. Note that these definitions make sense as long as the denominators are non-zero. Also, note that the conditional probability density function x given y is a function of x, and we assume that y is constant. Similarly, probability y given x is a function of y, and we assume that x is constant. We can similarly define the conditionals x given y and y given x in the continuous setting. The only difference here is now that we are going to be working with the joint probability function instead of the joint probability mass function. Also note that all of these definitions will make sense as long as the denominators do not vanish at y, which we assume is a constant in x given y, and x, which we assume is a constant when we are calculating the conditional distribution of y given x. Let us work an example. Suppose we have a random variable x which has the binomial distribution with parameters n and p. The random variable y has the binomial distribution with parameters m and p, and we assume that x and y are independent. Let z be the sum of the random variables x and y. Then we can show that z is going to have the binomial distribution with the parameters n plus m and p. We now want to calculate the conditional distribution of probability x given z. We will assume that x takes the value k and z takes the value s. In this setting, we are looking to calculate the probability that x equals k and x plus y equals s divided by the probability that x plus y equals s. We can rewrite this equation as follows and use the fact that x and y are independent to get x equals k and y equals s minus k to split. This simplifies under the assumptions of binomial distribution for x, binomial distribution for y, and the binomial distribution for x plus y to get the following expression, which might look complicated, but we can rearrange the terms to get it as n choose k times m choose s minus k times p to the k, p to the s minus k, 1 minus p to the n minus k, and 1 minus p to the m minus s minus k. And in the denominator, we have n plus m choose s times the following quantity, which actually cancels out with the numerator to give us that the probability x given z of k given s equals n choose k times m choose s minus k divided by n plus m choose s. Notice that this is exactly the hypergeometric distribution with a population of size n plus m, the number of successes inside the population being equal to small n, and we are sampling without replacement a sample of size small s. Note that for every s inside the set 0, 1, 2, 3 up to n plus m, we will get a conditional PMF Px given z of x given s. For a fixed s inside the set 0, 1, 2 up to n plus m, we can compute the expected value of x given z equals s. This is going to be equal to s times n over n plus m. This is called the conditional expectation of x, given that x plus y equals s. We can similarly calculate the conditional variance, which has a slightly more complicated looking formula. We will be using this formula very soon in today's video. Let's do another example. In this case, we are working with a joint PDF, that is x and y are continuous random variables. The joint PDF is given as 6xy times 2 minus x minus y on the interval x between 0 and 1 and y between 0 and 1 and 0 otherwise. Our goal is to compute the PDF for the conditional distribution x given y. To do this, we will first calculate the marginal for y. This is going to be equivalent to calculating the following integral, which, as you can see, very easily simplifies to y times 4 minus 3y. As a result, we can calculate the conditional PDF to be equal to the joint PDF divided by the marginal, and the resulting answer ends up being 6x times 2 minus x minus y divided by 4 minus 3y. Furthermore, we can calculate the expected value of this conditional PDF. This is going to be the integral from 0 to 1 of x times fx given y x given y dx. Notice that the conditional PDF is a function of x, which is the reason why we are integrating with respect to x. We can follow through this calculation to get the expected value of the conditional PDF x given capital Y equals y to be equal to 5 minus 4y divided by 8 minus 6y. This is the conditional expectation of x given that y equals small y. We will now introduce an interesting formula to get expectations using conditioning. Suppose x and y are two random variables, then we can calculate the expected value of x to be equal to the expected value of the conditional distribution x given y. This formula will be true as long as both of these expected values exist. Note that the expected value of x given y is with respect to the conditional distribution p x given y, or the conditional density function fx given y. Let's revisit our formula. The earlier example where we have x having the binomial distribution with parameters n and p, y having the binomial with parameters m and p, and z equals x plus y having parameters n plus m comma p. Recall that x given z equals s has the hypergeometric distribution with parameters population size equals n plus m, the number of successes equals n, and sampling without replacement a sample of size small s. The expected value of x given z equals s is exactly n over n plus m times s. If we want to think of this as a function of z, we will write this as the expected value of x given z to be equal to n over n plus m times capital Z. Now we can calculate the expected value of x given z. Working through this calculation and noticing that the expected value function is linear, so that constants come out, we notice that this is exactly, and then using the fact that z has the binomial distribution with parameters n plus m comma p, we get that the expected value of x given z to be exactly equal to n times p, which is the expected value of x, which had distribution binomial with parameters n and p. We will next work with a formula that lets us calculate variances using conditioning. For any two random variables x and y, we have the variance of x to equal the expected value of the variance of the conditional distribution x given y plus the variance of the expected value of the conditional distribution x given y. Note that this formula works as long as all the involved variances and expected values exist. Also notice that the variance of x given y and the expected value of x given y are calculated using the conditional distribution for x given y. To get a better sense of this formula, let us revisit our example where x had the binomial distribution with parameters n and p, y had the binomial distribution with parameters m and p, x and y were independent, and z equals x plus y had the binomial distribution with parameters n plus m comma p. Recall that x given z had the hypergeometric distribution with parameters population size equals n plus m, sample size equals z, and the number of successes equals small n. Now we work out all the ingredients required to check our formula. The first ingredient is the variance of x given z. Recall that this is a quantity that we previously calculated. We will then calculate the expected value of the variance of x given z. To do this, we will have to use the linearity property of expected values, and also notice that the expected value of the square of a random variable is exactly equal to the variance of that random variable plus the expected value of that random variable squared. Keeping this fact in mind and being very careful with our algebra here, we notice that we have a bunch of manipulations to work through, and I'm showing you how it follows through. Uh, Important thing to remember over here is things will seem very complicated for a bit, but everything eventually cancels out to give you the expected value of the variance of x given z to be n times m divided by n plus m times p times 1 minus p. We next recall that the expected value of x given z was calculated to be n over n plus m times z, so that the variance of the expected value of x given z ends up equaling n over m plus m times z, the variance of this quantity. And remember, whenever we take a constant out of the variance, it is squared, so we get the following cancellation, so that the variance of the expected value of x given z ends up equaling n squared divided by n plus m times p times 1 minus p. Now putting all of our calculations together, we notice that the expected value of the variance of x given z plus the variance of the expected value of x given z ends up equaling the following sum, which simplifies to n times p times 1 minus p times m over n plus n over n plus m. And this simplifies to n times p times 1 minus p, which is exactly the variance of x. This proves the variance identity in this very specific context. It is very important to do such examples to get a better grasp on many of these theoretical formulae. Just to summarize, we have spoken about conditional distributions. We have spoken about using conditional distributions to calculate expected values and using conditional distributions to compute variances. There were two important formulas that were stated. We'll be using these ideas in the next video, but this is all for now. Yeah. Take care of yourselves, and I will see you around.